Great. So welcome everyone to today's SIAM PDE online seminar. So it's really a great pleasure for me to chair Gautam Iyer's seminar talk today, because Gautam, besides being a great mathematician, is also a great colleague and a great friend. So I'm particularly happy to have today this duty to do so. So Gautam got his PhD in Chicago, under the supervision of Peter Constantine in 2006. Then he moved to Stanford, and then to Carnegie Mellon, where now is a professor. So I like very much your description of your research activity from your webpage, that you are a theoretical applied mathematician. And I also, took and made mine, in a sense, this description. So you take problem from, say, applied mathematics, but to do a theoretical treatment of them. And with combinations of tools from PDE theory, from dynamical system, from probability. And that's something that I guess we are going to see today in your talk about speeding up Langevin dynamics by mixing. And then the floor is yours, Gautam.
Thank you so much. Right. So thank you for this nice introduction and for inviting me to speak. It's an honor, right? And it's nice to see you. Right. So let me start out by saying, okay, this is, I'll eventually talk about some joint work with Alex Christie, who's currently a grad student at Penn State, Yuan Feng from East China Normal, and Alexei Novikov, who's also at Penn State. But before I get into our work, I thought I would just say a few words about some cute things. I'm a bit new to sampling and this sort of stuff. So I thought I would just say a few nice introductory things about this, right? So just an old problem in probability is sampling from a target distribution, right? So if I give you a weight function, P, right? How do you sample random points with the probability proportional to P, right? So this is long-standing open problem. I wouldn't say open. It's a long-standing problem with many applications. The prototypical example is this thing called the Gibbs measure, right? So in the Gibbs measure, my weight function P is really e to the minus beta times E, right? Where E represents energy of being in configuration X, right? And beta is inverse of temperature, right? So why is this hard, right? So it's, like I said, it's a long-standing problem. So the reason it's hard is because typically my state space is huge, right? So if I'm only telling you weights, right, this weight function P, in order to convert it to a probability density function, I need to normalize it. So I need to compute sum of all the weights. And that's this normalization constant Z over here, right? And if my state space is huge, right, this sum is very hard to compute, right? So that's one reason why this is not good. The other reason is, look, quite often your weight function is concentrated in a very small region of the sample space. Right, I'll show you how as we go along. But if the weight function is concentrated in a very small region, in order to sample well, I need to find these regions where the weight function is concentrated. And finding this is hard. There's no obvious way to do this. Right. So there's this nice paper by Percy Diaconis in 2009 called the Markov chain Monte Carlo revolution. Right. It's very accessible. Strongly recommend it. But just to say what this discrete thing is, right? So let me pretend the state space is discrete and call pi of x to be the weight function P divided by the normalization constant Z, right? So the idea in this Markov chain Monte Carlo sampling is cook up a Markov process whose stationary distribution is pi. Right? So just to remind you, this means that, well, if I look at the law of the Markov process as time goes to infinity, I should expect that my law converges to the distribution pi. And pi is the distribution I want to sample from. Right? So this philosophy is hey, look, I draw samples from distribution pi by starting with some possibly bad initial distribution mu, and then run this Markov process. Right? So if I run it for long enough, I'll get close to the distribution pi, and there we go. So of course, as you probably see, well, I was a bit iffy about if the chain is designed well enough, then it converges to the right stationary distribution and you can sample, right? How do you design these chains? There's an industry of such algorithms. The first one that I know of is the Metropolis Hastings algorithms that date back to the 50s, which is super simple. I can explain this in 3 lines, and it's amazing how well it works, all right? So this Metropolis algorithm says, well, okay, let's pick some distribution, let's call that capital Psi, that I can sample from, right? So I want to sample from pi, I don't know how. I pick something, let's say uniform, that I can sample from, right? And then I do the following. Okay, so suppose my Markov process is currently at state little x. Yeah. Then I choose a new state, y, randomly, according to the distribution that I can sample from, right? And I do this accept reject decision, right? Which is I jump from x to y with probability 1 minimum the ratio of the 2 weights, right? So P of the new location divided by P of the old location, right? And otherwise, I just stay at my current location, right? So this is a super cute thing. It works amazingly well. There's, like I said, there's this nice accessible introduction. Let me show you one application before I go on to this continuous stuff I was going to talk about, right? So this application in this 2009 paper that Percy cites was how do you unscramble text, right? So here's this old method of coding, which of course nobody uses now, right? Which is, suppose I have a message and I want to scramble it by just replacing the letters, right? So for instance, replace A with R, B with Z, etc., right? How do I unscramble this, right? So if I try a brute force permutation search, this is impossible, right? So I have 26 letters, 10 numbers, punctuation, so let's say 40 odd symbols, right? So brute force to figure out how to unscramble the letters is 40 factorial permutations, right? So try all of these until you see something that doesn't look like nonsense. This is not tractable, yeah? However, I can do something a bit smarter, right? So I have statistics on frequencies of letter combinations, right? So for instance, U always follows Q, etc., right? So I know something. So I can do this, use these statistics and run up Metropolis in a nice way, all right? Turns out all you need is like 2,000 iterations for it to converge, right? And here's, I mean, let me actually show you this thing working, all right? So these 2 students of Percy's at Stanford, right, started out with I guess the bottom line is the text from Shakespeare, right, from Hamlet. They took it and they started out with known text and scrambled it. So the first line is the scrambled version, right? And you can see, right, the way this thing converges in about like 1,500 iterations, and maybe a little bit more, 1,800 iterations, right? It's almost got the right thing, right? And I mean, I find this very striking. This is something, right? If I'm searching in a state space of size 40 factorial, and I find what I'm looking for in like 2,000 iterations, that's amazing, right? So yeah, that's a quick introduction, if you like. But now I'm going to spend most of the time talking about continuous state space, which is stuff that I'm a little bit more familiar with, right? So what happens to this in the continuous setting? Okay, so my state space is RD, right? In RD, the way I cook up the wake function is as follows, right? I take a potential capital U, which is typically known and regular, right? And let me choose kappa to be a small parameter, right? And I want a sample from a distribution whose weight function is e to the minus u over kappa, right? So minima of the potential u is where my weight will be the highest, and then away from the minima of the potential u, my weights will be exponentially small. So let's normalize this to the to a PDF, right? So call pi to be rho infinity of x dx, right? Where rho infinity, I call this to be the weight function p divided by the normalization constant z, right? And z is just simply integral of p, right? So how can you sample from this? Of course, there's an industry of algorithms. I won't talk about all of them. There's Metropolis Hastings, Hamiltonian Monte Carlo, Langevin Monte Carlo, etc. So let me not go into all of these, right? What I'd like to spend most of my time about is talking about one of these, right? This Langevin Monte Carlo, right? So like I said, so this paradigm is design a Markov chain, or in this case, a Markov process, since it's continuous space, continuous time, whose stationary distribution is the one I want to sample from. And there's a very nice way to do this in the continuous setting, which is use the Langevin equation, right? So what's the overdamped Langevin equation? So I've written it up here, right? It's just dx is minus gradient of u being the same potential from before, right? Plus square root of kappa, square root of 2 kappa, dw. Right, so w is Brownian motion, right? Kappa is a small parameter, right? The physical interpretation this comes from is, suppose I'm studying movement of a particle that's subject to Newtonian forces that you typically see from this gradient of potential term, right? And small random forcing, which I see from this noise term. And typically in the Langevin equation, you also have friction, right? Now, what I'm looking at here is this overdamped limit, right? So what you do with the overdamped limit is you send the friction coefficient to infinity, and you also rescale time, right? So when you do this, that friction term drops out, and the equation you're left with is what I have in the box, right? So nice thing is for this equation, I can just write down what the stationary distribution is, right? It satisfies this nice forward equation and solve it, right? The stationary distribution is exactly the distribution I wanted to sample from, right? Which is the density is proportional to e to the minus u over kappa, right? So just to introduce notation, I call rho infinity to be the density, which is e to the minus u over kappa divided by z. Z is your normalization. And I'm going to call pi the invariant distribution as a measure. Yeah. Okay, so now I know that if the distribution of my process capital X, of my Langevin equation, right, converges as t goes to infinity, to the measure pi, then I just simulate x for a long time, and it allows me to sample from pi, right? And of course, the faster my distribution converges to pi, the sooner my samples become good, right? All right, so does the distribution converge, right? So I've been mixing the notion of density rho infinity and the measure pi, so apologies, I should fix this, right? All right, so what's known? Well, if U is strongly convex, then it's known when the distribution of X converges to pi at some exponential rate. More generally, if there's a Poincare inequality or a log Sobolev inequality, then also the distribution of X converges to pi exponentially, but there's a catch, okay? So even though it converges exponentially in time, the Poincare constant may be huge, right? When I say huge, let me quantify it. It may be of size e raised to plus 1 over kappa. Yeah. So what this means is that, look, even though it converges, it's going to take a long time to converge, right? It might take e to the plus 1 over kappa time for my distribution to be reasonably close to my stationary distribution. And of course, this is an important problem. People have studied this for a long time. There are many, many, many strategies to improve the convergence rate, right? There's tempering, there's biasing, non-equilibrium sampling, there's branching, right, etc. What I'm going to be a little bit too stretched if I describe too many of them. So I'm just going to focus on one idea, right, which is this one idea of using mixing. Okay. This is an idea that I guess some of us have been working on for a while in fluid dynamics, and it's nice that it has use applications. Right? So, all right. So first thing I want to do is I want to say, let me, instead of working on RD, I want to compactify the space. Let me work on the d-dimensional torus. Okay. On the d-dimensional torus, Poincare inequality always holds, right? So I'm guaranteed that as time goes to infinity, my distribution of my process will converge to the stationary distribution exponentially. Okay. However, Poincare constant is still huge, e to the plus 1 over kappa. Yeah. So a priori, I'm only guaranteed that I have convergence, but at this very, very slow rate. You see that? So e to the minus t times e raised to 1 over kappa, right? So that's slow. So our main idea is that, hey, look, if you add a mixing drift into this, I'll tell you exactly what I mean by that. You can make the convergence an order of magnitude faster, right? And I'll tell you exactly what I mean by that as well. And of course, as a mathematician, I'll say, hey, look, I've solved the problem. Add a mixing drift, you made the convergence faster, wash your hands. But that's not useful in practice unless I give you an example, right? So I'll also give you examples of the mixing drift explicitly. Right. Okay, so before I do this, let me quantify what you mean by rate of convergence. The probabilists do this, have done this for a long time. They use this notion called the mixing time. And let me quote that here, right? So remember, pi is the density of the invariant distribution, right? The mixing time, typically denoted by T mix, is the smallest amount of time I need to wait so that the difference between the distribution of my process at time t and the stationary distribution in the total variation norm is some constant less than 1. I'm going to use half over here to normalize, right? Maybe 1 over e is better, but some constant less than 1. Yeah. And again, the mixing time is measured with this really strong norm, right? So I use total variation distance between distribution of my process and the stationary distribution, right? Okay, so again, why this, right? So if you look, if I have the Markov property, right, say, hey, look, if after time t mix, I've gotten half away from the invariant distribution, then I can just iterate this, right? After time 2t mix, I've gotten 1/4 away, right? So after time t, right, my distance from the invariant distribution decreases exponentially. How fast? It's like e to the minus t divided by t mix up to a constant. Yeah. So this just measures, all I'm saying is this measures the rate of convergence of your distribution to the invariant distribution under total variation norm, right? And the point I'd like to make is that if U has multiple wells, so I've drawn a picture here. So here's a picture of a potential with multiple wells. This is perfectly symmetric, right? If it's multi-welled, I claim that the mixing time has to be of order e to the plus 1 over kappa, right? This is sharp, you can't really improve it, right? Why is this? Because you see, the mixing time, I want my distribution to become close to the stationary distribution for any starting initial distribution. Yeah. So if I start, for instance, in the shaded orange region, right? So I start at one of the minimum of the potential well, right? Then it's going to take me a really long time to get out of this potential well, right? The noise is very small, right? Size kappa, and the potential keeps pushing me back in. So I basically need to take a whole bunch of steps in the same direction because of the noise to jump to the other well. And that's where you get this e to the 1 over kappa factor from. So it's not going away, right? So the point is that, well, if I started out with a bad initial distribution x naught, right, I really have to weight e to the 1 over kappa in order to get good quality samples from Langevin Monte Carlo, right? Unless I do something else. Okay, so here's one of the suggestions of something else, right, which is add a drift, add a mixing drift, right? So I took the overdamped Langevin equation, which is written in black, right, which is dx is minus gradient u dt plus square root 2 kappa dw, same thing as before. And I added a drift in red, right? So w of x dt. So what's this drift, right? So first thing I want to do is I want to make sure that my new equation has the same stationary measure, right? So this is easy enough to do. All you have to do is check that your drift satisfies a divergence condition, right? So explicitly, the convergence, the condition is here, right? So I need kappa times divergence of my drift to be gradient of the potential dotted with the drift, right? All right, so if I have this and I preserve the stationary distribution, can you improve the mixing time? All right. So there are a couple of things. So the first thing I should say is that when you add a drift like this, you don't slow down convergence, right? And that's part of some of the results I've quoted here, all right? But not only do you not slow down convergence, you can actually improve it significantly. So there's some results. So I'm not going in chronological order, but maybe in logical order, right? There's this first result by Demark, Frank, and Jacobi, and said, okay, suppose my potential U is quadratic, right? If my potential U is quadratic and my dimension is 2, then they produce a sequence of drifts. I'm going to call them Wn over here, such that the mixing time of with the drift Wn converges to 0 as n goes to infinity. So they can make the mixing time arbitrarily small. Okay, but again, this is specific to the quadratic potential, and the quadratic potential already you don't have this e to the 1 over kappa annoyingness because you don't have to jump from one minimum well to the other minimum well. But regardless, it's nice that they can make the mixing time arbitrarily small, right? Then there was a bunch of papers by, okay, so L'Elviare, Pavliotis, Duncan, right? Gullian, Monomark, Liu, and Spiliopoulos, right? Apologies if I pronounced some of the names wrong, right? So what people did in this bunch of papers is they choose the drift W to be an antisymmetric matrix J times gradient of the potential. So basically what this means is if I look at level sets of the potential, I'm going to explore the level sets fast, right? I'm not going to change the level sets, right? What they found, right, is that, look, this helps convergence. It reduces the mixing time from e to the big C over kappa to e to the little c over kappa with a smaller constant little c, right? So it's good, improves the mixing time, but it's still exponential. Yeah. What I'd like to talk about is, hey, look, if instead of choosing W to be this skew symmetric matrix times gradient of U, let me choose W to be a rescaling of some mixing drift, right? So V is something which is going to be exponentially mixing in the sense of a dynamical system, which I promised to tell you on the next slide, right? Or maybe in 2 slides, right? Capital A is a rescaling parameter, which I'd like to play with, right? So I want to speed up the time of the velocity field, right? And I want to increase the amplitude in a way, well, for reasons I'll tell you about in a second, right? So if I do this, so what can we prove, right? I say, okay, I can find you an A naught. This A naught depends on dimension. It depends on kappa, right? and I can estimate the mixing time, T mix, explicitly in terms of the mixing rate of the velocity field V and capital A, right? And what happens, but I'll show you the estimate, right? As capital A, the amplitude goes to infinity, mixing time goes to 0, okay? But again, I realize that as a mathematician, again, I would say, hey, look, mixing time goes to 0, I'm done, but not quite, right? When capital A is large, it's very expensive numerically, right? So I don't want to make A large. I want to choose A to be as small as possible. So let me choose A equal to A naught being the smallest amplitude under which the theorem works, okay? So if I choose A equal to A naught, what happens, I can plug it in and compute, the mixing time turns out to be of order dimension divided by kappa square, so polynomial. So I've changed this e to the 1 over kappa to something that's grows linearly with dimension and like 1 over kappa square, okay? I can give you examples of V which are reasonably simple, well, which theoretically should be simple to implement. I'll write them down shortly, right? There's one thing that we cannot do, which is how big is A naught, right? So there's a guess that we have for A naught, right? And the guess is that A naught should be like 1 over kappa square times square root of dimension. We cannot prove this guess. I'll show you where this guess comes from. It basically depends on the mixing rate, how the mixing rate depends as kappa goes to 0. This is something that we don't have control on, right? If you believe this guess, then let me also tell you, so the extra computational effort that's going to come from solving this equation is through this W term, and that W term has size d over kappa cube, right? So you've reduced the mixing time to something that's polynomial by adding a drift, which is also something of polynomial size, okay? All right, so what does this mean? So this hinged on adding this velocity field, which was exponentially mixing. What does that mean, right? And I realize at this point that I'm mixing notions, right? Which is we have mixing in the sense of Markov processes, and then mixing in the sense of dynamical systems, and we're kind of mixing both of them over here. So let me just say what these are and highlight the difference, right? So first, right, for the dynamical system, there's no noise. Let's go back to ODEs from undergraduate, right? So look at the flow of the vector field V, right? So time derivative of capital phi equal to V composed with phi. That's the flow. You start with initial data to be the identity map, all right? Now, again, I want this dynamical system. I shouldn't say dynamical system because V could be time dependent. So that's my fault. So I want this flow, capital phi, to preserve the same stationary measure, right? So my stationary measure is pi, and phi preserves the stationary measure if and only if the same divergence condition holds, right? Which is kappa times divergence of V is equal to gradient of U dotted with V. Okay. So what does mixing mean? Okay, so let me start with some initial distribution mu naught. Okay, the notion of mixing for Markov processes is start with your distribution mu naught, run the Markov process. After time t, distribution of my Markov process converges to my invariant distribution or stationary distribution strongly, no matter what initial distribution mu naught I chose. Right? So when I say strongly, I mean total variation norm, right? And any mu naught could be a delta measure, could be something horrible, right? Yeah. So what is it in the sense of dynamical systems? So for dynamical systems, I'm going to start again with the same initial distribution mu naught, push it forward by the flow of your dynamical system after time t. So again, since it's time inhomogeneous, right? I say, okay, start the flow at time s, push it forward to time s plus t. So flow for time t, right? So for a dynamical system, for mixing, what you want is that the push forward after running it for time t converges to the invariant distribution weakly for regular initial measurements. Right? So the difference is I went from strongly to weakly, and I went from any mu naught to regular mu naught. So why did I do this? Right? So first, right, for dynamical systems, since the measure pi is invariant under the flow, it's an immediate check, right? So if I start with any measure mu, push it forward by the dynamical by the flow phi, right? The total variation difference between phi star of mu and the stationary measure is constant, doesn't change with time, right? So there's no way I can have the push forward of mu naught converge to the stationary distribution strongly for dynamical systems. That's impossible. So I have to do it weakly, and that's fine, right? Also, suppose your initial distribution was a delta measure, right? So if I start with the delta measure and push it forward by the flow of the vector field B, right, it's going to stay a delta measure for all time. Yeah? So you see, there's no way this delta measure is going to converge to the stationary distribution in any notion, right, weakly or whatever you want, right? So the problem being, if you start with something that's too localized for a dynamical system, you might not get convergence, right? So you have to start with something a little bit more regular, and that's why I said initial data being regular, right? So that's the difference between these two notions. How do you quantify it compactly? Right? The way you quantify it compactly is look at decay of correlations, right? So I want regular measures. So what I'm going to do is I'm going to use regular test functions. Okay. So f and g are just test functions. Take one of these two test functions and push it forward using the flow of the vector field B, right? Test it with the other test function g, which you hold constant, right? So you want these correlations. I'm going to assume that all test functions are mean zero, right? So I don't know if you can see clearly, but this dot on the top of L2 means L2 means zero. Yeah. So if f and g were two mean zero test functions, then if I run the flow for a long time t, right, I expect that these correlations should decay to zero. The rate at which they decay is your mixing rate, right? So that's what I've put over here, which I'm highlighting in green. D times e to the minus kappa t is my mixing rate. And again, since I want, this only happens for regular test functions, you see, so I put on the right-hand side a stronger norm of f and a stronger norm of g, right? Not just L2 norms. Again, so these inner products are all with respect to the stationary distribution pi, right? And L2 dot is L2 means zero. Yeah. Okay. So what's the mixing time bound, right? So the mixing time bound, as I say, okay, let's look at the overdamped Langevin equation with the drift as we have here. My exponentially mixing assumption says the correlations decay exponentially with rate. So capital D is the prefactor, and minus gamma is what goes inside the exponential. Okay. So what we can prove is, I say, I'm going to choose A naught as follows, right? So A naught is, if you look, gradient of the velocity field comes in the numerator, right? So the larger that is, the larger A naught has to be. Gamma comes in denominator with a square, right? This gamma is the same as the gamma in the exponent of the mixing rate. And I have log of the prefactor square, right? So if I choose A naught by this formula, right, right, just note that capital D and gamma may depend on kappa, which is the reason that I don't know exactly the kappa dependence of A naught, right? So if I choose A naught by this formula, what we can prove is the mixing time, right, is bounded about by, if I look inside the brackets, the largest term inside the brackets is 1 over kappa. So norm of U oscillation is maximum of potential minus minimum of potential. Since I'm working on a compact torus, maximum minus minimum of potential is something finite. Okay, so this thing times T dis. T dis is this dissipation time, which I bounded above. So it turns out that T dis is bounded by norm of gradient V 1 over gamma square times capital A times log of A times capital D divided by norm of gradient V. All right. So again, you can see, right, from this equation that I've written here for the dissipation time, if I hold everything else constant and I send capital A to infinity, as I send capital A to infinity, clearly this right-hand side converges to 0, right? I have 1 over A times log of A square, yeah? Right, so once you have the dissipation time, you can bound the mixing time in terms of that. And then, of course, I can substitute in. I don't want to choose A to be as large as possible. I want to choose A to be as small as possible to help the numerics. So I plug in A equal to A naught. And what do you get? You get dissipation time of order 1 over kappa, mixing time of order 1 over kappa square. Right. So I'll tell you what dissipation time is in a second. Right. That's like an L2 notion, right, which I'll describe next. Yeah. All right, so before I describe what it is, let me just say, so what's the idea behind the proof, right? So people have studied mixing times a lot in probability, and I spent some time trying to read their techniques and learn their tricks, right? So I couldn't use them, right? I tried my best, right? So these coupling tricks and the Cheeger bounds, etc., don't help. The Poincare, log Sobolev, etc. tricks help, but they give me a very bad constant. The thing that helps is the Fourier splitting methods that we use in PDE all the time, right? I use these Fourier splitting methods to bound the dissipation time, which is an L2 thing. And then I bound the mixing time in terms of the dissipation time, which is sufficiently general, right? So how does this work, right? So what does dissipation time do? It measures the rate of convergence in L2, not total variation, measures the rate of convergence in L2 if my initial distribution was also L2. Okay, so one way of saying this is I say, okay, let me start with a mean zero L2 initial data, theta sub s. Okay, then run my Markov process X for time t, right, and look at theta s plus t to be expected value of the Markov process after time of theta s applied to x after time t, right? So this is the standard thing you do when you look at the Kolmogorov backward equation, right? So if my Markov process x is mixing, right, then as time goes to infinity, right, theta sub s plus t should just converge to integral of theta s, which is 0, because my test functions, I just want them to be mean 0, right? So I know that theta s plus t converges to 0 as time goes to infinity. Dissipation time is basically the amount of time I need to wait so that my L2 norm drops by a factor of half. Right? You see, I know L2 norm is converging to 0. Wait, how long do I have to wait until it drops by a factor of half? Yeah. And of course, so this is this notion that's very useful in PDE, right? I guess I got this name from Albert Fanjang's paper in 2003. I'm not sure if other people use that, right? But yeah. This dissipation time is related to the mixing time in a sufficiently general way, right? If I look at the mixing time, I can always bound it below by 1/3 of the dissipation time, and I can bound it above by dissipation time times a little bit extra. So why do I need a little bit extra, right? So let me just think about it this, right? So mixing time is I measure convergence starting with horrible initial distributions, completely localized, right? So what do I need to do, right? I say, hey, run the Markov process for a little bit of time. If the noise is reasonable, it's going to regularize. It's going to become L2. But once it regularizes, the norm could be really large, right? So 1 over kappa typically. So you pay a price, right? And that's the price you pay, right? So regularize it. Once it's L2, I know that if I wait for some multiple of the dissipation time, I can make it as small as I want. So look at how big I've become because of regularizing. Take the log of that, and that's the price you pay. And that's what I've shaded in green. This works in other contexts too, right? For instance, if I did it in Lebesgue measure instead of the measure pi that I wanted here, the price you pay is basically log of kappa times the dissipation time, right? Okay. So in the event of time, right, let me not go into the details of the proof, right? Let me just say the idea behind the proofs is you split into, if you have high frequencies, right, then the diffusion operator lets you dissipate really well. If you don't have high frequencies, use the fact that your drift is mixing, right, to generate high frequencies and then dissipate them, right? And this is a trick that's been used quite a bit in PDEs, right? There's a really nice paper by Konstantin Kiselev, Rizhik, and Zlatosh in 2008, which I strongly recommend reading, right? So, yeah. So let me spend the last maybe 10 minutes or so saying what these flows are, right? I said, if you add an exponentially mixing drift to the Langevin system, right, then you can bound the mixing time by something that's a polynomial, right? So that looks like it's good from the purposes of sampling, but it's only good if I can tell you what to add to the system, right? So how do you construct these? So a purely deterministic construction of exponentially mixing drift is hard, right? People in dynamical systems have studied it for a long time. So this time independent, this thing goes back to Anosov, Polycurt, right? These nice papers of Dima Dolgopet and Leverani proving exponentially mixing of, they're all time independent vector fields. They work on these axiom A flows or geodesic flows. They work on manifolds, right? So this is hard dynamical system literature, right? There are also more recent results motivated by people in fluids, because we care. I mean, fluids are time dependent, so we loved dependence in time, right? And even then, it's really hard to construct exponentially mixing examples. So here are a few. There was one by Yao and Zlatosh in 2017, one by Gianluca Crippa, Anna Mazzucato, and Giovanni Alberti in 2019, Tarek Elgindi and Andrei Zlatosh in 2019, right? So these are recent, right? And they all appeared in fancy journals, so they're not easy to do, right? So, but I don't want to do those because those are too hard, right? I'm going to use a random construction. Now, the thing about random constructions, right? So there are these random constructions which quote unquote mix almost surely, right? These things are known for a while, right? They date back to Halmosh in 1944. He only did flows, right? But then Furstenberg, and then these ideas of Baxendale and Struck from 1998, Kaloshin, Korolov, Dolgopet, right? And then these nice papers of Jacob Bedrosian, Alex Blumenthal, and Sam Cushion-Smith that showed up a few years ago, 2022, right? So the point of all these random constructions is the following, right? You can construct a family of velocity fields, which with probability 1 will mix exponentially as a dynamical system, right? And what I'd like to do in my situation is take this example of Pierre Humbert, who did it for fluids in 1994, right? And adapt it to our situation for the Langevin system, right? And the good thing about everything that's been done for random dynamical systems is to check mixing. I can reduce the problem to checking certain irreducibility conditions, right? So this is technical and it's a bit of suffering, but it's doable, as opposed to dynamical systems where you really need some sort of divine inspiration. And even once you get it, it's very problem specific. If you change the flow or you change the measure, you need, again, this divine inspiration, and that's hard, right? But checking irreducibility conditions, I mean, that's just suffering, right? You sit with the door closed for a little bit, and it's not pleasant, but you can do it, right? So how does that example work? Let me show you what goes into it, right? So again, so remember, the measure preserving condition I need in this case is I need kappa times divergence of my velocity field to be equal to gradient of the potential times v, right? another way of saying this is that I need to say divergence of my velocity field that I add times my weight function p is equal to 0, right? So remember, p is just e to the minus u over kappa. Let me give you an example in 2 dimensions of something that I can use. Okay, so constructing divergence-free things in 2 dimensions, we know how to do that. Just take the skew gradient of a stream function, right? Well, now I want p times v to be divergence-free. So I say, okay, take the skew gradient of something and divide it by p. That gets you something that's perfectly divergence-free, right? Now, I didn't quite do that here, right? Because if I just took skew gradient of psi and divided by p, this is actually not good for numerics, right? Because p, if you remember, is exponentially small away from regions of interest. So if I take some reasonable stream function, take its skew gradient, and divide it by p, numerically, this is going to be horrible because in most of the space, I'm moving with huge velocity, which is hard to control numerically, right? So instead of just taking a stream function, taking the skew gradient, dividing by p, what we did was we took the stream function, multiplied by p, take the skew gradient, and then divide by p, right? So the reason for doing this is because, hey, look, now, I mean, things cancel, right? So this skew gradient is just the skew gradient of the stream function. That's the first term. And the second term, well, gradient of p divided by p, well, p is an exponential. So gradient p over p is just gradient of u, right? So the second term just works out to be stream function divided by kappa times the skew gradient of the potential. And that's something of order 1, right? So again, let me also point out, right, the whole reason that you run into trouble with these Langevin systems is if your potential has multiple wells. If your potential has multiple wells, you might get stuck at a second minimum, right? Let me just do this idiot test look, right, at the drift V that I'm constructing, right? At a potential well, gradient of u is 0. So the second term vanishes. The first term does not. That's my extra string function I've added, right? So this thing can kick you out of these metastable equilibria of the potential. Once it kicks you out, right, hopefully it lands you somewhere good, right? So it's not easy to make a proof saying, hey, look, just take something that's non-zero at the potential wells and then you're okay, right? Because if it takes you out, it might bring you back in later. That's why we use this whole mixing assumption, because I'm guaranteed it's going to take you away and not be too bad in long term. Okay.
Gautam, you wanted
yes,
a 45 minutes. You wanted a 45 minutes warning, and that's
thank you so much. Now. Right, I promise the rest of my slides are basically pictures and references. So hopefully, I'll finish. Right, right. So, right. So now that we have this trick to construct velocity fields that should be useful and mixing, right? Let me use it, right? So what I'm going to do is I'm going to choose my stream function psi as follows, right? So let me choose capital F to either be a sine. This is sine is what Pierre Humbert did, or alternately a periodic sawtooth. So sawtooth is the picture that I've drawn on the right over here, right? Yeah. And then what I'm going to do is randomly shift it left or right, and then randomly change direction. So either use this profile to act as a shear in the vertical direction or act as a shear in the horizontal direction, right, randomly, and then shift it, right, and also add an amplitude, which is random, right? So precise formula is that I'm going to define my stream function psi to be my shear profile f acting on either first coordinate or second coordinate randomly. That's why I put in, with a shift, which is random, that's the alpha n, and an amplitude that's random, that's the beta n. All right. So choose all of these IID uniformly distributed, and at integer times, just make a new choice. Right. If you want to do this in d dimensions, you can do the same thing, right? Just pick ith coordinate and jth coordinate randomly, right? And once you have the stream function, plug the stream function into this formula here for the velocity field, right? So if I was doing this on the torus with respect to Lebesgue measure, all this corresponds to is a shear in the horizontal direction and shear in the vertical direction. This is exactly those ideas of Pierre-Humbert, right? If I'm doing this for the Langevin system, it's not quite a shear, right? Because this P could depend on all coordinates. So when you take this, it becomes a little bit worse to solve numerically, but it's still doable. Then you go turn the crank of these random dynamical systems, and you can check the velocity field V is with probability 1 exponentially mixing. And then I can, of course, rescale it and use this to reduce T mix, right? So then I promised you some pictures. So let me show you some pictures. All right. So top left is a picture of level sets of a two-dimensional potential, right? So I take a two-dimensional potential U, and then I take e to the minus u over kappa, with kappa equal to 1 over 70, right? And I do the level, we drew the level sets here. Yeah. This middle picture, which I'm just highlighting, is what the streamlines of the velocity field V look like when my shear is in the vertical direction. So my stream function only depends on the x1 coordinate, right? So you can see, right, probably we should have overlaid the stream plots, the streamlines of P a little bit darker. I tried to overlay them, but maybe we should do this a little bit darker. I'll change that, right? So you can see what the streamlines of V look like, right? So they don't get stuck in the local minima of the potential. They move, right? But they also don't directly take you from one to the other, right? And then we ran some simulations. So here's the simulations if I just run the Langevin system, right? So what am I doing? So to run this Langevin system here, I started with all the samples to belong to one of the potential wells. Okay, so if I start with all of them at one potential well, I run it. In this case, we ran it for time 3. You see the number that I found the other potential well is really, really small. You can see just a handful of them, right? The middle figure is what we did with our drift setting, right? So we add this exponentially mixing drift, run it. In this case, I ran it for time 0.6, and already I've found a whole bunch of them have jumped out of the first potential well and found the second potential well. Then I ran it, we ran it for the same amount of time, right? This 3.14 is coincidence. It's not designed to be pi or anything like that, right? But okay. And you see it's almost 50-50, equal distributed between the two, right? So I guess we also had simulations. If you want to try use this to do Monte Carlo integration, you can also see it does converge faster. Let me just, rather than going through what these are, let me just point out, to do the numerics, we found it was better to, instead of switching the shear direction discretely at times, like alternate times, you switch it continuously in time. Right? So that worked out better numerically, right? Let me maybe stop by saying what we cannot do and what's important to do for future. The mixing rate constants. So this theory of dynamical systems, random dynamical systems, tells you that you're almost surely exponentially mixing, but it doesn't tell you what capital D and gamma are, right? I don't know how capital D and gamma behave as kappa goes to 0, right? The reason I want to know this is because if you remember, my formula for the amplitude A had D's and gammas in it. It had 1 over gamma square and it had log of capital D, right? So I want to make gamma large and I want to make D small, and that would help the numerics, right? Are there better choices for the mixing drift, right? So we use this example of Pierre-Humbert. I don't know if other ones are better. In the numerics, we even use this continuous time version of that worked even better, right? Can we do it on RD instead of the torus? So some of it, yes, right? So we can bound, for instance, dissipation time. If you give me an exponentially mixing flow, right, then we can bound the dissipation time. However, these random dynamical systems things that we looked at don't quite work when your state space is not compact. So we couldn't find these flows that were exponentially mixing on RD, right? And even if we did find them, the bounds that we have are for the dissipation time. They don't give you the bounds on the mixing time. There's a little bit more work to be done to get that. And finally, most important would be numerical schemes. So we make no mention of numerical schemes for this. Discretizing the system is, there's a huge industry of people studying discretized schemes for this. There's this Jordan Kindle error, Otto, there's scheme, etc. Right? Let me just point out, in our situation, when you have the Langevin equation with the drift is large. It's not small, right? It's of order 1 over kappa cube, right? It's necessarily chaotic. It's not something nice. If it was something that just follows level sets, it's not going to help reduce the mixing time, right? So on the time scales of interest, this drift is mixing, right? So it's good to reduce the mixing time theoretically, but it's expensive numerically, right? So can we estimate the bias? Can you estimate things like asymptotic variance? We don't know how to do this. What I suspect is this is good for is that when you run these Markov process sampling things, you want to spend some time initially rapidly exploring the state space. Something like this will help you. Once you do that, then you can just turn off the drift and run one of the other algorithms because you get better accuracy out of those. Right. So thank you so much. Sorry, I ran a few minutes over time, right? And I have a bunch of references which I can share. Right.
Great. Thank you, Gautam. So that was very, very, very interesting. And I think we still have some 5 minutes or even a bit more time for questions. So maybe I'll start with the curiosity, since I don't see any raised hand or anything in the chat or in the question and answer. So something is coming now. So how much does this rely on the fact that the mixer is an exponential mixer? Meaning, so if you had a slower mixing rate, would you be able to somewhat improve, but not so much the?
Yeah, actually, so we did do this in the paper, which I didn't want to say in the talk because I thought it would just be complicated. If you give me mixing at some particular rate, I can tell you what the mixing time is as a function of the mixing rate. Right? You have to take some inverse function and solve an implicit equation. So, but yeah, absolutely, we can do that. Right. So and of course, the slower the mixing rate is, the larger this capital A will have to be, right? Sure. So more expensive numerically.
So we have a question in the chat. So by Jianfeng Lu, could you please elaborate a bit the relation of the mixing shear flow with the level set of U?
Absolutely. So let me go back, right? So if I look here, right? So the papers before, in fact, I think your paper, right, with Costas, when you look at this antisymmetric matrix times gradient of potential, what happens is the drift goes along level sets of the potential, which I'm trying to draw, and I'm not succeeding, but maybe I should stop, right? Here, the drift that we add does not respect this, right? It crosses level sets of the potential in a bad way, right? So it goes like, it crosses these streamlines. And so as a result, I mean, actually, we want it to cross the streamlines because I don't want it to get stuck at this local minimum here. And it's nice that the drift can transport me. And that's what you kind of see from the second figure and the third figure, right?
Thank you. So any more question, either in the chat or live. So just unmute yourself in case. Otherwise, I have maybe another very naive curiosity. So, did you talk with people doing machine learning or neural networks? So this question about sampling and this fact that you have very, high dimensional landscapes with a lot of minima. Of course,
So
you have dynamics there.
I'm doing my this is absolutely the right question. Thank you. Right, I'm doing my very best to do this. So to be perfectly honest, we managed to finish this paper and post it on Monday, 3 days ago.
It's a lot of
So
time.
yeah, it's on my list of things to do.